So for an example, a track for a tractor made up of 120 links. Each length is produced with a nominal length of 12 inches and a tolerance of plus or minus 0.0125 inches. Question then, what is the tolerance expected on the total length of the track? So if you let T equal to the tolerance of the total track, then the total tolerance is going to be equal, T is going to be equal to, now you've got here, we said the total tolerance is going to be equal to the square root of the sum of all the different tolerances squared. Oh, they're all the same. So that is the same as saying 120 times T squared. Let's call it T1 squared. They're all the same. And that T1 is, all of them are 0.125 inches. And you end up then with the value of 1.37 inches. So the nominal tolerance on the track length will be, in total, the whole length will be 1440 inches. That's your 12 times 120, plus or minus 1.37 inches. Here we have an assembly where we have a part D, which is kind of an indentation, shall we say? And in it, we're putting three parts, part A, part B, and part C. And these all, we know how long the indentation is. It's 4.5 plus or minus 0.02. And we know how long each of these A, B, and C places are, 1.5, and 1.75. And so each of these have their tolerance here of 0.01. So this is LA, TA, LB, TB, LC, TC, and this is LD, TD. So the question then is, what is the expected tolerance on the gap? And here we have our gap, L gap, and T gap. We don't know. So now the nominal value then of your gap is going to be the overall length, this LD, 4.5, minus the sum of the individual lengths here, 1, 1.5, 1.75. So we get that the L gap has a nominal or expected, we expect it to be 0.25 if everything is perfectly on target. But the tolerances then for the gap is going to be the square root of all the individual tolerances added together and squared. So what we have here is 3 times these 0.01, 0.01, and 0.01, the tolerances for A, B, and C, because they're all the same, plus squared value 0.02 of the tolerance for D. So again, we have to sum them, even though here they're subtracted. Here we have to sum the variabilities for all components. And we get the value of 0.026. So this means the gap will be able to meet a specification of 0.25 plus or minus 0.026 in total. Now let's look at this again. This is the same example. If the customer requires a tolerance of plus or minus 0.02 on the gap, what proportion of the assemblies will be outside specification? So again, we assume the lengths of the parts A, B, C, and D are all independent and normally distributed. And we assume, now this is the important part, we assume that the tolerances are based on 3 times the standard deviations of the individual lengths. So back to our normal distribution. We have then, we said the tolerances are, like for A, for example, is going to be 3 times sigma A. And tolerance for B is 3 times sigma B. And now these are lengths we're talking about. So we're saying that the length of A, the length of B, the length of C are all normally distributed with mean and standard deviation for A, etc., etc. This variance, I should say, mean and variance for C. So this is what we are assuming. So that means simply, since these are all equal, the sigma is going to be the tolerance divided by 3. Because we're saying that the tolerance is 3 times sigma. So solving for that, we end up for all those parts, L, A, B, and C, the sigma, the variation, the standard deviation for these parts is 0.0033. And likewise for the long gap, the tolerance was plus or minus 0.02. So you divide that by 3 to get sigma D, standard deviation for part D. And then, again, you can add the same way we did before when you have the sum or the difference of random variables that are normally distributed. You end up with 3 times the tolerance for each individual length plus 3 times 0.0033 squared for each individual length plus 0.0066 squared for the LD, and you get an overall standard deviation for this gap, or overall variability for this gap, sigma equal to 0.0087. So now the specification limit, since it's on the other page, was 0.25 plus or minus 0.2. This is what the customer has given us. So here we're looking at 0.23 and 0.27 as your lower spec limit and your upper spec limit. So given that, now the question is just as we did before with the normal distributions, what is the proportion out of specification given that we have this overall tolerance or overall standard deviation for the gap. So we're looking for 1 minus the probability that we're within these two specifications, 0.23 and 0.27. And so if you go ahead and convert these to your Z values and look things up in your Z table, you find out that 2.14% of the assemblies will have gaps that are either too small or either too large. So, a little repeat there, but we just want to do one last topic. Specification limits or tolerance limits usually refer to the limits of variability that a customer has imposed. These are based on where and how the application or how the product is going to be used. They may have been given to you already by the customer, or they could be chosen by the designer based on his or her assessments of the customer's requirements, or even based on a previous technology. So we may, however, sometimes want to know what tolerance limits a process is capable of meeting in its current condition. And these tolerance limits, which reflect actually the capability of the current process, are called natural tolerance limits, or NTLs of the process. And these are chosen as a 3 sigma tolerance. So as mu plus or minus 3 sigma. And here we have the little hat here. This is indicating you need to have an estimate of the mean and this is an estimate of the characteristic mean using that particular process and an estimate of the standard deviation, the actual true standard deviation of the current process. So when are these useful? Well, first of all, you can get these types of values. You can take samples. Actually, your process is running. You've got a condition. You take samples, preferably a number fairly large, greater than 50, and then you can go ahead and calculate these estimates using, take the overall sample average and the sample ranges we've done before. Or the sample standard deviation, and then you can give yourself an estimate for the natural tolerance limits for that process. And they're useful then when you want to study also, is your process able to meet the customer specifications? If they fall within the specifications given by the customer, then you have good capability. Otherwise, you need to work on your process. And NTLs are most useful when you're setting tolerances for process variables and in process product variables. So For the process variables, you have characteristics of the materials or subassemblies of the product at the intermediate stages of the production. These are things the customer will not see. So you don't need to, or you don't have any specifications for the customer, but you need to see how well how your process is running, and then you can control it with that. So for an example, you have maybe making tires, and you have different rubber sheets that are used for layering the tire. And so this is an important variable. The thickness of these sheets is an important variable in the tire production, and you need to have a uniform thickness over all the sheets, and you need to make sure this is consistent then to produce quality tires. The customer, though, is not interested at all in knowing the target for those sheets or the tolerance for the sheets. They're interested then in the final overall thickness of the tire and the overall quality of the tire. So the process engineer for this example would choose tolerances for the sheets as natural tolerance limits, and then that would then go into your overall final tolerance limits for the final tire, and you see if that meets the customer specifications.